Hi there, this video is all about my UNI-T UT210E clamp meter. The UT210E is very affordable and because of its Hall effect sensors can measure DC and AC currents. Its lowest range of just 2 amps and 1 milliamp resolution makes it ideal for electronics and finding earth leakage currents in the house. But this is not a review of the meter, there are plenty of these already. This is about recalibrating it. I recently noticed that its current readings were way off. The spec says 2% for DC and 3% for AC, but this is more like 10% under reading and needs fixing. By the way, the problem is only on currents. Volts and resistance ranges are absolutely fine. As you can see, the zeroed meter reads 980 milliamps instead of about 1 amp. The first thing to rule out is residual magnetism of the clamp itself. Hall effect sensors are sensitive to any magnetic fields, and over time the clamp itself can become magnetized from the current carrying wires it measures. So it's good practice to demagnetize, also called degauss the meter regularly. I use this blue demagnetizer from China, which produces a very strong magnetic field changing direction at mains frequency, and by moving the meter away from it, the magnetism induced by this constant pole-changing magnetic field gradually diminishes in strength, leaving the meter demagnetized. Once demagnetized, the clamp meter needs to be zeroed again to compensate for the Earth's magnetic field. The reading is slightly higher than before, but still way too low. So residual magnetism is not the problem. This meter is seriously out of calibration. To test the accuracy of the DC current readings, I run a DC current from one of my bench power supplies through a 10 ohm resistor and compare the readings of the UT210E with the Bryman BM869S. Not too exciting to watch in real time, so I speed this up a bit. By the way, the resistor box is another of my projects and has proven incredibly useful, not just for this test. If you have not seen it, I add a link to the video about building it. I need to repeat the test with AC current, but with what I have in the lab, it's quite hard to produce variable AC currents above 100 milliamps or so. For this test, I therefore use a transformer that has 6 taps, which allow me to get most of AC voltages from 2 to 24 volts in 2 volt steps. Because I have to disconnect when changing taps, the current always drops briefly to 0 in between tests. If you are interested, I show more of this power supply in a video which I'll link in below. Here are the results in a spreadsheet. I added graphs to make it easier to see what's going on. For both AC and DC current, the blue trace of the UT210E deviates more and more from the green trace of the BM869S, the higher the current gets. The red trace shows the error in percent on the right axis, and it quickly increases to around 7%. So how to calibrate the UT210E? It's done using a cal menu entered by pressing some buttons during power up. But what I've read on various blogs was not encouraging. There are stories of people losing their calibration completely, and that the reference values you need to apply during calibration are hard to produce accurately. Since all calibration data is stored in EEPROM, I thought it prudent to back up the content before I try my luck at changing the calibration. You can connect to the EEPROM using one of those 8-pin SOIC clips after carefully bending some of the MOVs aside to make room. But I must confess, that did not work for me. My clip just did not make reliable contact to the EEPROM, possibly because of interference with the crystal housing next to it. While it might be possible to shave off some of the plastic from the clip's housing to get a better fit, I decided to try another way, which worked. I use a USB-driven bus pirate module to access the EEPROM, connected to a cable with a 2mm pitch 6-pin connector on the end, in which I put a strip of 5 pins of 2mm pitch pin headers. You can see that the PCB has space for a 5-pin programming connector. My cable fits directly into this, and although not soldered in, the pin headers make good enough contact to access the EEPROM. As you can see, the programming connector corresponds directly to the EEPROM pins, and the address lines are pulled to ground anyway. I try to show the connections necessary for use with a bus pirate. It will work the same for other programmers. There are 3 things to note. To be able to change the content, you need to pull the WP or white protect pin to ground. Conversely, it needs to be connected to VCC if you want to white protect the content. For the bus pirate, you need to connect the VPU line to 3.3 volts for the pull-up resistors to work. This is specific to the bus pirate and may not be needed with other programmers. The third is that the meter should be turned on. Just move the selector switch to the first position from off. The meter won't work, of course, because with the back off, the battery is disconnected, but that's okay in this case. The address lines of the EEPROM are all set to ground. These actually select the bank address. If you have multiple EEPROMs on the bus, each needs to be set to belong to a different bank. The first byte sent to them is the control byte, where the upper 4 bits are always 1010. The next 3 bits select the bank, and the last bit determines if you want to read or write. Since the bank address are all set to ground for the UT210E, the EEPROM responds to the control byte of hex A1 for reading data and to hex A0 for writing, each followed by the address of the desired byte within the 256 bytes bank. You can use a bus pirate interactively using a terminal program, but it also has a binary mode where it can be controlled by a computer. I wrote a little Python script to use bus pirate to read the complete content of the EEPROM in my UT210E, and this was the result. My original intention was to use this as a backup, and if anything goes wrong, I could simply use the dump to restore the EEPROM to its original state. But now that I have the data, I was curious about its meaning. It turns out a chap called Carrie Wong not only found the Chinese datasheet of the processor chip DMT0660 used in the earlier versions of the UT210E, he also did a brilliant job in translating most of it. Newer UT210Es use a slightly different chip, DM1106EN, but still use the same layout of the EEPROM data. The main difference is that the newer chip, which is also in my meter, can do 9,999 counts for all ranges, while the older one does a maximum of 6,000 count for the current, volts and resistance. You might be surprised to hear that because the UT210E is a 2000 count device in all ranges, but it turns out it is simply artificially throttled down in software to distinguish it from other UNI-T meters that have the higher display count. The key section of the datasheet is the breakdown of how the data in the EEPROM is used. There is a section shown in blue here that maps the buttons and range switches to functions. For example, you can change what the default mode is. Right now the meter starts with AC and you need to press select to go to DC. You can change that by reprogramming the corresponding entries in the EEPROM. But I did not feel the need and will skip this part in the EEPROM map. Instead, I'm more interested in the calibration data and how the display count is set. This is another view of the selected area of the dump of the data of my UT210E. Most of the data is in fact 16-bit words, and the way it is stored is low byte first, followed by the high byte. As an example, the value at address hex 10 and 11 is 70 and 17 respectively. This is a 16-bit word, so we need to swap the bytes and get hex 1770. Converted to decimal, we see 6000. So this is the default count of the meter. The value in brackets is the standard value or initial value. The addresses 1213 hex and 1415 hex reveal how the UT210E was throttled down to 2000 count. The upper range limit is simply set to 2200 and the lower range to 190. So when the display exceeds 2200, the UT210E will switch to the next higher range even though there is no hardware need. For a 6000 count meter, the appropriate values would be the highlighted 6200 and 580 values for the range limits. We'll cover whether changing those values is a good idea in a bit. First, we need to get the calibration sorted. There is no point in a higher display count if the measured values are wrong anyway. The cal values for current start at address hex 50. Because this chipset is intended for 6000 count, the values are referred to as 6 amp, 60 amp and 600 amps, even though the UT210E the ranges are 2 amp, 20 amp and 100 amps. The first surprise is that the 600 amp or 100 amp range was never calibrated from the factory, since it still has the default value of hex 8000 or 32,768 decimal. So how does the UT210 calibrate? It's surprisingly simple if you consider this example. A true value of 800 milliamps is applied, but instead of 800, the UT210E reads only 650. First, we calculate a correction factor, CF, which is the reference divided by the measured value. So 800 divided by 650, which is about 1.231. To store this floating point in the EEPROM, it is simply multiplied by 32,768, and all digits after the decimal point are dropped. In the example, we would have a value of 40,330 or hex 9D09, and that value is what you would find in the EEPROM. Once the value is set in the EEPROM, the meter simply applies the correction factor to all measured values before they are displayed. So the same internally measured 650 is now shown as 800 because 650 times 1.231 is 800. Mathematically, the correction factor rotates the blue trace around the center point to match the green trace. It is now also easy to understand the significance of the hex 8000 or decimal 32,768 default value. This value is simply correction factor of 1. In other words, the measured value is identical to the displayed value. I want to mention a blog post by Alva-Deb on this forum in Russia to point me in the right direction in understanding how this works. If we go briefly back to the content of my EEPROM, we see the cal value of 36,505 for the 6 amp range. This means the correction factor is 36,505 divided by 32,768 or 1.1140. And back to the spreadsheet earlier, we can observe that what we need to fix the problem is indeed a rotation of the blue trace to match the green one. So let's explore this a bit further. We know the current correction factor of 1.1140 from the EEPROM is obviously not right. I put it down here in blue. So let's get rid of it by dividing the values in column C by that factor, and we now see the raw values the UT210E was actually measuring internally. This is the column D. Now that we have the raw measured value and the reference value from the BM869S, we can calculate the correct correction factor that we actually need. This is column E. It helps to plot the value of column E to get an idea on how the values are spread. Theoretically, it should be a horizontal line, that is, regardless of the measured value, you would get the same correction factor, but it is of course impossible as there are all kinds of measurement errors to consider. We can see, however, that the value should be somewhere around 1.2 and not 1.1 as it is now. We could use the AC or DC measurements for finding the best compromise correction factor, but I favor the DC measurements because the AC values are fewer and they have the inherent problem that the mains voltage and thus the transformer voltage and therefore the current is always varying. So it's problematic to compare readings from two instruments. You read one and when moving your attention to the second one for comparison, the mains value may have changed already. On the DC value, I discount the very beginning where measurement errors are always proportionally largest and came to an average correction factor of 1.2038 in yellow, which converts to a rounded new cal value of 39,447. Because of the rounding of going through the conversion for storing it as a 16-bit value in the EEPROM, the effective correction factor based on this cal value is the green value, which is slightly different from the yellow one. If I use the new correction factor and the measured values, I can calculate what values the UT210E calibrated with that new value would have displayed in column F, and column G finally shows the percent error that freshly calibrated UT210 would have had. The difference to before is staggering. For most of the values, we stay well below the 0.5% error. Note that I apply the same correction factor for both AC and DC because there's only one value in the EEPROM used for both. Now this is all spreadsheet magic, so I decided to go ahead and change the EEPROM cal value for the 6 amp range to the one we just calculated. I thought I'd save you from watching another set of measurements comparing the readings of the calibrated UT210E and the BM869S for DC and AC currents and go directly to the result graphs. Above the horizontal line in the middle are the previously uncalibrated results, while the graphs at the bottom are the new test results. The blue and green lines are almost on top of each other and the error is significantly reduced. This is very encouraging, and I decided to repeat the same procedure for the higher current ranges. It's basically a repeat of what you have seen already, so I only focus on what's noteworthy. To begin with, I have no means of producing reliable AC or DC currents of tens of amps and very limited ways of measuring them accurately for comparison with the UT210E, so clearly I need to improvise. When I tested the current transformer for scopes on a previous video, link below, I used the trick of using multiple windings for making the transformer think the current was higher than it really was. To see if the Hall effect sensors of the UT210E fall for the same trick, I measured a moderate current through a single wire, about 0.68 amps. Now I make a loop so the same current goes twice through the UT210E clamp. And sure enough, the display is now double, even though the current is still the same. So here's my test setup to measure the DC 20 amp range. It's basically a repeat of the 2 amp test, but the wire carrying the current loops 10 times through the UT210E clamp, so when the BM869S reads 1 amp, the UT210E should read 10 amps. And here's the same for the AC 20 amp range. After both AC and DC measurements are complete and in a spreadsheet, I followed the same procedure shown earlier to first remove the wrong 60 amp correction factor, then calculate the new correction factor for each value, pick a suitable average correction factor and apply that instead. Now for currents beyond 20 amps, I considered using thinner wire to add more turns on the clamp, maybe 50 would be feasible, but a lot of work. Instead, I decided to keep my 10 windings and up the current. After all, I normally don't need currents that high, and UNI-T did not even bother to calibrate this range, so anything I do is probably an improvement. For more current, I need a smaller resistor to keep losses and heat controllable. The resistor here is about 0.5 ohm, and with my bench DC power supply I can put 5 amps through this, which means I get good coverage up to 50 amps DC. Because my AC voltage goes only in steps of 2 volts and choosing 6 volts already seriously overloads the transformer, I can run this test only very briefly, but at least I managed to put about 8.8 amps through the 10 windings of the UT210E, so we have an 88 amps AC as another test point. In hindsight, I could have simply used the current going through a mains-driven fan heater directly to get 10 amps or more, but I did not think of that. Here are the results before calibration. You can see that the error of around 7% for the 20 amp and 100 amp range is pretty much similar to the one I had in the 2 amps before I did the calibration. In all cases, we have the case of the blue trace diverging more and more from the green one when the current gets higher, and a simple recalibration with a new correction factor can fix this. While I was doing the patching of the 60 amp and 600 amp cal values in the EEPROM, I decided to try changing the count from 2000 to 6000 as well. I don't have a formal test for the higher current ranges as I did for the 2 amp range, just some samples to check everything works as it should. 20 amps in the 20 amp range, and now it can read 30 amps as well. Before it would have shifted to the 100 amp range already. 40 amps, still in the 20 amp range, and 50 amps. A quick check, the 100 amp range shows 50 amps as well, so all is good on the DC side. A similar test for the AC currents. 31.6 amp in the 20 amp range, 50.7 amps in the 20 amp range. Testing the 100 amp range shows 50.7 amps as well. And now we read correctly 89 amps in the 100 amp range. While I'm happy with the calibration results and the count extension from 2000 to 6000 seems to be okay, there are some questions to be asked. You see here part of the spec of the UT210E, and the part that's important is the statement about non-sinusoidal waveforms and how the accuracy degrades with increasing crest factor. I made a whole series of videos about ohms and the different waveforms, and I put a link for a video that you should definitely watch to understand the crest factor. In a nutshell, the crest factor is a measure of how bumpy or spiky a wave is. It is the ratio between the peak value and the ohms value. A pure sine wave has a crest factor of 1.41, and a square wave has the lowest possible crest factor of 1. So with that in mind, how to read this spec? A sine wave has 1.41. Should I add 3% error? But this is for non-sinusoidal forms. How does the chip know whether a waveform with a crest factor of 1.4 is a sine wave or not? And by this statement, even a wave with the lowest possible crest factor of 1 may cause 3% extra error. This whole statement doesn't make much sense. The problem is that complex waveforms with a high crest factor can have significant peak values but a comparatively low ohms. In today's electronics, pulses are far more common than pure sine waves, and being able to handle a sizable crest factor and still showing the correct ohms value is important. In the UT210E, as in many other meters, there is some signal protection and clamping, but then everything is done inside the chip. There isn't a traditional range switch or AC coupling capacitor to block DC in the AC ranges. Here, for example, is a sample DC pulse with 20% duty factor. This example works with volts, but the same principle holds for current as well. For a DC coupled device, the peak is 8 volts and its overall ohms is 3.57 volts. This, the UT210E has to be able to process and calculate the ohms shown by an AC coupled device, such as traditional AC multimeters, which is just 3.2 volts. So although we only see 3.2 volts on the display, the AD converter has to cope with 8 volts. In the older UT210E, the DMT0660L chip has a 14-bit analog to digital converter, and if we assume that in the volt range the least significant bit corresponds to 1 millivolt, a signal that can be converted without error would have to be within plus minus 8.191 volts. So a pulse like this represents about the maximum a meter using a 6000 count mode could handle correctly, even though the shown ohms value of 3.2 volts is barely over the halfway mark. If the pulse amplitude increases even more, such a meter will show incorrect values. With the original throttling to 2000 count, this cannot happen because a signal like this would have long forced the meter to switch to the next higher range. Based on a 14-bit AD converter, the spare headroom for the ADC in 6000 count mode is too small to handle any even mildly spiky signal correctly. Now I tested this case and my meter can handle this and much higher voltages without problems in 6000 count mode. My guess is that the chip DM1106EN used in newer UT210Es has an ADC with at least one additional bit. Let me freeze this video for a moment to explain what you see. The white box on the left is basically an H-bridge that I built to generate accurate AC square waves. There's a video about it which I'll link in below. In this setup I only use it as a half bridge to generate pulses, and it's set to be externally controlled by my function generator set to 20% duty cycle. The reason I use this box here is that it allows pulse amplitudes of up to 400 volts, simply determined by the voltage I apply on the H-bridge. The waveform of this setup is basically what you just saw earlier in a drawing. So at the moment the peak voltage is 14.4 volts and both the BM869S and the UT210E show the same RMS of 5.33 volts. If I increase the pulse amplitude beyond this value, the UT210E basically freezes while the BM869S keeps increasing as it should. If I decrement the amplitude below the 14.4 volt mark, both meters show the correct RMS values. Here's a scope picture of the same test. At 14.4 volts and 20% duty cycle, we see an overall RMS of 6.18 volts, but both meters show the AC coupled RMS, which is just 5.3 something. If you didn't know there are different kinds of RMS, I refer you to my RMS video I mentioned earlier. Anyway, what happens is that if I increase the pulse amplitude beyond 14.4 volts, the UT210E AD converter can't follow anymore and remains stuck at 14.4. Effectively, the meter's signal processing is clipping the pulses, and since they remain rectangles, the shape and therefore the calculated RMS stays the same. A ceiling of 14.4 volts means it can handle a crest factor of up to 2.32 in 6000 count mode. Not brilliant, but okay for many tasks. It's probably a good idea not to use the full 6000 count when measuring AC volts or current with unknown waveforms. There are three known issues or quirks with the 0 button on the UT210E. The first, using 0 stops auto range from working. I'm demoing this with DC volts, but the issue applies to other modes as well. You can see that when I go above 6 volts, the meter switches range as expected in 6000 count mode. And back again when I drop below 5.2 volts, so far so good. If I select a small voltage below 1 volt, say 500 millivolts, and zero it, the UT210E is now locked in the millivolt range and I get an overload error when applying 1 volt. The second issue is similar in that auto range is disabled, but this time I zero the display while measuring 2 volts in the volt range. If I now increase the voltage, I get an overload when going above 4 volts, but in reality that's really over 6 volts because we are basically subtracting 2 volts from the display. You can see that we have really over 6 volts if I cancel 0 by a long press. It has to be long or you just zero out the current value. You could argue that it's relatively rare to use the 0 button in a multimeter, but in a clamp meter for DC current you basically have to use it because of residual magnetic fields causing a current to be shown even when no current is flowing. Unfortunately, the current mode suffers from an additional bug that in zeroing the meter it reverts back to 2000 count. So when the current exceeds 2.3 amps or so, you get an overload. You can cancel 0 and then the meter will go back to 6000 count. That means you have to mentally subtract the 0 value from the result. There is another workaround called dotless display involving reprogramming the EEPROM to use the 6000 amp range for 6000 milliamps. For now I've decided to skip that, but I leave a link in the description where you can read all about this and other hacks for the UT210E. Finally, what about the cal menu? You have to press select and hold together and then turn the meter on. It shows cal and then launches into some kind of self-test. Which fails apparently because at the end it shows error 0, and that is it. The only thing you can do now is to turn the meter off and back on to reset. I have not found what error 0 means and whether it's even an error, but it seems it's not uncommon, so I decided to ignore it. It is possible to abort the self-test by pressing select before it finishes. So that's the fancy cal menu. The DC volts certainly ignores my 5-volt reference. Select brings us to ohms and it seems to hunt for a resistance. Another pressing of select and now it looks for capacitance. And now we are back to DC volts. Maybe it does not like the 5 volts, but 0 volts doesn't change anything. And shortening the leads in ohms mode is equally useless. Let's try some real resistors, 1K. Interestingly, now the DC volts is showing some stray voltages. But the ohms mode is confused with the 1K. It does not seem to settle on anything and keeps hunting. And a 10 nanofarad capacitance in capacitance mode is no good either. I am very unimpressed by this. I was very careful not to press 0 or hold because these buttons apparently acting as plus-minus buttons to select a value for calibration, and without knowing what it expects to see at the input, that could be destructive to your existing calibration as it happened to some. I did check my meter and it appears that the cal settings are still intact. I think the method of calculating the cal value in a spreadsheet and then changing the EEPROM is far easier and better. In addition, you can change all kinds of other things like the count or backlight or auto power off to your liking. Thanks for watching.